Hey everyone, and welcome back. Before we begin here today, please make sure that you like and subscribe because it really does help out our channel, and it also really does help us reach others in need of assistance with these topics. So this will be our first video in our structural analysis series, and we're going to be starting with statically determinate beam reaction. So this structural analysis series and the static series on this channel will have a little bit of an overlap, but overall, the structural analysis series will be made up of more complex and longer problems than the statics problems. So, statically determinate. All statically determinate means is that we can use our standard equilibrium equations of summing forces in the x, summing forces in the y, and summing moments about a point, all equaling 0 to find all the reactions that we need. So that means that we can only have a max of 3 reactions for a member to be statically determinate. Any more than that it is considered to be statically indeterminate, and we will eventually start posting videos on that topic. So we are going to find the reactions for our beam here. Our beam has a fixed condition right here at point B, which just is shown by it sticking into a surface. So pretty much with these types of problems, whenever it's sticking into a surface, such as a wall, in this case, it looks like, or the ground, it is to be considered a fixed element unless told otherwise. Now, in real life analysis, you would have to double check or even triple check to make sure that that surface, that wall, that ground, whatever that beam is sticking into is strong enough and capable enough to actually turn that into a fixed reaction point. But here we're just going to safely assume that it is a fixed reaction point because, well, there's no other reaction point anywhere else. So with a fixed cantilevered reaction here, we're going to have 3 reactions occurring at this point. We are going to have a vertical one, which we are just going to assume in the upward direction. So B sub y is upward. We have a horizontal one, which we are just going to assume to the left, and that would be B sub x. And then we are going to have a moment reaction here, which we are going to assume clockwise, and we're going to denote that as Bm. Now, before we start using any of our equilibrium equations, we have to do one thing, which is the trick with this beam in order to solve it. Well, we have this 10 kips here apply to E. Well, E is elevated off of point D. As you can see, they have some welds going on here, so it is not a single member all the way through D. It is extending beyond our member of AB here. So this 10 kips will transfer down into point E as it currently is in the downward direction, that amount. However, because it is cantilevered off here from this vertical position, it is going to create some type of rotation here, and it is going to create a clockwise rotation of this entire portion when it goes from this end to the center here, and then down into D, this moment will be transferred all the way to point D. So this 10 kips, which is now elevated off of our beam, creates a 10 kips vertical downward force at point D on our beam, and it also creates a moment there, and that moment is going to be the value of 10 kips times the distance it is away from D, which is 2 feet, which gives us 20 kip feet of moment right here. So that's one of the tricks that you have to watch out for with this particular beam. Now, with this 10 kips transferred down to D and along with its moment, we don't need that original drawing there, and we don't need that extension from D to E as well. Now everything is along our beam. Okay, so now let's start using our equilibrium equations to solve for our reactions. We have 3 reactions that are unknown and 3 equations to solve for them. So let's start with the easiest one, which is usually the easiest one, is summing forces in the x direction. We're going to take everything to the right as positive. Well, this 3 kips per foot, which is a uniform load, the arrows are pointed downward, so it is vertical. The 10 kips is vertical, 20 kip feet's a moment, By is vertical, and Bm is also a moment. B sub x is our only x force there, so it has to be equal to 0. There is nothing for it to react to. So that's an easy one. Boom, done with the x direction. Now let's do the y direction. We'll take upward as positive, and everything in the y direction has to cancel and be in equilibrium, so thus being equal to 0. So let's start with our uniform load over here, which is 3 kips per foot. So anytime you encounter a uniform load, you want to take its magnitude, which is going to be 3 kips per foot, and you want to multiply by the distance that that uniform load runs, the distance that it is spanning along the member. Well, that uniform load goes for a total of 8 feet. This right here will give me an equivalent point load for this uniform load, which is the equivalent point load is just basically 3 kips per foot times 8 feet, because it's saying 3 kips per every foot. And how long does it run? Well, it runs for 8 feet. So that would give me how much kips is actually being exerted by this uniform load. Another way to think of it is that you're just finding the area of how much loading is there. If the height is the magnitude and the width is the length that it runs, you're finding the area of that load. Well, this 3 kips per foot uniform load is acting downward, so it's minus. And then we have the minus 10 kips over here as well. The 20 kip foot is a moment. Don't include it. We have b sub y. We have it assumed upward. And then lastly, nothing else in the y direction. So that's everything equal to 0. When we rearrange here, we get our y direction to be exactly 34 kips. It came out to be a positive number. So that means that my original assumed arrow direction of up was correct. Which let's actually make that look like an arrow direction going upward there. You know, that is pretty poor. Let's just do that. There we go. Boom. So anytime you would get a negative answer for your reactions, that just means you assume the wrong direction. So you just would drop the minus sign and flip the arrow. But since this one came out positive, that means it is truly upward and I assumed correctly. All right, so now we're on to the last one, which is our moment one. And we are going to sum moments about point B. It doesn't really matter where you sum moments. Everything should be in equilibrium here. But summing moments at your reaction point usually is the better case to do so, because your reactions that you just found or you're going to find will cancel out right there at 0, because their perpendicular distance would be 0 to their point that they're moving through, so they don't create any moment there. So this really takes away that possibility of having additional errors, because what if you sum moments over here at A and you got B sub y wrong? Well, then your moment here, B sub m, would also be wrong just because you screwed up B sub y. So summing moments at your action point kind of takes that away and helps you out a little bit more. So you don't have to worry about that possibility of screwing up even further. All right, so going through our moment equation here. So let's start with our moment, which we assume as Bm, and we have it going clockwise, and we're taking counterclockwise as positive, so it's minus Bm. And then let's just work from right to left here. And then we would have our 20 kip foot moment. It is also rotating clockwise, so it is minus 20 kip feet. It doesn't need a distance because it's already a moment. And then we have our vertical load of 10 kips here. Well, it is going to be moving counterclockwise about point B, so plus 10 kips. And then I need a distance to get it over to point B. Well, at point D, it is now 5 feet away. So there's my distance. And then lastly, my uniform load, which would be 3 kips per foot times 8 feet. And then I need a distance to get it over towards point B. Well, this equivalent point load that we found earlier, which is just the area of the rectangle, it will always act at the centroid of that load. Well, what's the center of a rectangle? Well, the center of a rectangle is just half the distance from the edge. So this distance would just be 8 over 2, which is 4 feet. So the total distance to get it over to B would be 3 plus 2 plus 3 plus 4, which gives me a total of 12, because we would have 6, 8 plus 4 gives me 12 feet. And it will be rotating counterclockwise about B, and we're taking counterclockwise as positive, so boom, plus 3 kips times 8 times 12. And then that's all I have for my moment equation, which is equal to 0. So B sub m is the only unknown in this equation, so we can easily solve for it. Just take B sub n to the opposite side. And this would pop out to be 318 kip feet. It came out to be a positive number, so I know my original arrow direction of clockwise was the correct direction. I assumed correctly. So therefore, I found all my reactions. I got B sub x, B sub y, and my moment there at my reaction. Now, as with all reaction problems, you can always check these reactions to make sure that they are correct. And the way to do that is just by summing at a different point along your member. So let's go over here. Since we summed at B, let's just sum over here at point A to check our answers, to make sure our reactions and everything will cancel out and have equilibrium in the moment for this point A. So we're going to use our check, and I'm just going to put this in blue. Summing about A equal to 0. And I'm going to try to squeeze it in down here at the bottom. So let's just rewrite this real quick, because this was, what, 3 feet, I believe. So this is 3, this is 2, this is 3, and this is a total of 8 all the way across there. Now we can actually see it and scoot down here. All righty. So summing moments at point A, let's just move from left to right. Well, we would have our uniform load of 3 kips per foot times the distance that it runs, which is 8 feet. And then I need a distance to get it from its center to point A. Well, the distance from its center to point A will just be the 4 feet, which is just 8 over 2. This thing is rotating clockwise about point A, so that would be minus in front of it. And then the 20 kip feet is already rotating clockwise, so minus 20 kip feet. Don't need a distance there because it's already a moment. And then we have our 10 kips, which is also rotating clockwise, so minus 10 kips. And the total distance to get it over there will be 8 plus 3, which is 11 feet. And then we will have our moment right here, our reactionary moment, B sub m. It is rotating clockwise, so it is minus 318 kip feet. Once again, don't need a moment, or don't need a distance because it's already a moment. B sub x is 0, don't include it. And it also, you wouldn't have included anyways if it actually had a real value to it, because it goes right through point A. Well, and then the last thing we have is the B sub y right here. It is going upward. It will be rotating counterclockwise about point A. So that will be plus B sub y times its total distance. Well, let's just go ahead and throw in B sub y because we actually know what that is. 34 kips times its total distance over to point A, which is 16 feet. And that is all I have in my moment equation. And everything that is rotating about point A that has some type of distance or value in moment. And this should all cancel and be 0. And what does it do? Well, it does cancel, and it all equals to 0. So with all my reactions canceling out there at a different point and equal to 0, I am pretty confident that they are the correct answers of B sub x of 0, 34 for B sub y in the upward direction, and then my moment reaction at point B is 318 kip feet in the clockwise direction. So just keep in mind, whenever you are doing reactions, you can always check by summing moments at a different point, and this would be very useful if you have a test, homework, or a final exam. So I hope this video was helpful, and if you want to see more problems solved this Friday, please check out other videos on our channel, as we are going to start uploading more structural analysis videos, so bear with us as we build up our inventory in that topic. Also, if you haven't done so already, please like this video, leave a positive comment below, and subscribe to the channel because all of that does help us. Thank you for watching, and I hope you have a great day.